This is the buffer overflow attack presentation. The shellcode presentation will come tomorrow. Before we can talk about the actual attack, we need to talk a little about how the CPU works. This should be all a bit of a reminder from previous courses, but all we're concerned with here really is the dispatcher and the instruction pointer. The dispatcher is what handles switching context between different processes in the CPUs when a new process is loaded. All we're concerned with on that is that the instruction address is stored and usually in the stack. The instruction pointer is what takes that address, executes, or sends the instruction set to the CPU. That gets executed, the instruction pointer puts in the next address, and it loads that from the RAM. We also need to talk about the memory architecture for RAM. Now, it's really complicated, and for this we only care about the control and data sections. The control section is where all of those instruction sets that get sent to the CPU are stored. They're pretty hard to change from outside the computer. We also care about the data, namely the stack section. The stack stores local variables and, more importantly, that return address we just talked about. The stack is where most buffer overflow attacks happen. So let's look at what happens when a normal operation or process is called. The current address that the CPU is working on gets stored in the stack somewhere. The new process gets called in, put into the instruction pointer, and starts going. It's allocated with a certain amount of RAM. Now that new process finishes, the return address is loaded back into the instruction pointer, and the normal process resumes. Buffer overflow attacks take advantage of one major flaw in C and C++. It doesn't have a built-in RAM allocation. And what I mean by that is when a process is called, it is given this much amount of RAM by the dispatcher. But it doesn't actually have anything that checks if that process is using that amount of RAM. So during an attack, what will happen is the current address is stored in the stack as the return address. The new process begins and a certain amount of RAM is allocated. And then during that process, there's a call to store local variable in the stack. But it doesn't check that that local variable is way too big for what it was actually allocated, and it gets stored anyway. That data overflows into surrounding areas, overwriting the nearby data. And then the process finishes and that return address is loaded, but it's changed from its original value because it got overwritten by that variable. So why does that matter? Well, let's use the diagram here, and for this we'll assume A is the intended RAM allocation for the program and B is the location of the return address. Now they're adjacent to each other, so when that overflow happened, it overwrote B, it overwrote that return address. So instead of 0 being loaded into the instruction counter saying, hey, go back to whatever you were doing, it loads E into the counter. Now normally, this is fine on its own, it'll usually crash your computer, whatever the program is, but there's nothing that comes from it. But buffer overflow is an injection attack. It's meant to pair with other attacks, other malware. Because now the issue is threat actors have directed your controller to a takeover attempt. Somewhere else in your computer they've injected another thing and they've just directed your instruction set to go there and start that process. Obviously, as these attacks became more prevalent, we started figuring out ways to fix them. But before we talk about the mitigation, there's a couple things you should know first. The net explanation was incredibly simplified. The actual attack is heavily based in math and knowing where certain address registers are and memory allocations are. It would be spreadsheets and spreadsheets of knowing where things are and knowing exactly what to put in that variable that gets stored in the stack. For the mitigation strategies, you have address space randomization. This basically means randomly moving around parts of the data section so the attacker can't know where that return address is. They can't know where the text is to upload what else they need to. Next, you have the data execution prevention. This flags certain areas of the memory as non-executable. It doesn't really apply here, but it'll come in the shellcode presentation because remember, overflow attacks are an injection. They're supposed to be paired with something like shellcode. Then you have structured exception handler overwrite protection. It checks that certain data is not tampered with before and after the process execution. So before a process starts, it'll go and check that return address and say, hey, yep, looks good. And then after it, it'll go and check that return address again. If it's the same, cool. If it's not, then it throws up certain flags and it pauses everything.